So what I'll be talking about today is based on joint work with Han Le at Michigan. And I'll be talking kind of about two projects. So sort of the background for all of this, the key question that was our focus in coming at this project is what happens to the free energy of spherical spin glasses near the critical temperature threshold. And so I'll talk more about what all of those things mean. But there were a few recent breakthroughs in this area. So from 2016, some work by Jinho Baik and Ji-Yoon Lee. And then Ben Landon also has some recent work in this area, as well as another paper by Johnstone, Klochkov, Onatsky, and Pavlishin on a similar topic. And so theirs looked at the spherical Sherrington-Kirkpatrick model. And what I'll be talking about in my work is the bipartite spherical spin glass model, which is related to that one. And I'll go into more of the details. But what I wanted to mention up front is that when we try and do this analysis on the spin glasses, there was a missing ingredient that we needed, which was a certain statistic for random matrix eigenvalues, and that wasn't in the literature when we started working on the spin glass project. And so we took a detour to prove this CLT, and that'll be what I talk about in the second half. So it's kind of two different projects that I'll be talking about. So I'll start with just some background and then go into the results for the bipartite spin glasses, and finally this random matrix project that we did along the way. So starting from the beginning, one of the classical models that people look at in spin glasses is the Sherrington-Kirkpatrick model. And this is the setup for that one. We start with n particles labeled 1 through n, and each particle is assigned a spin, either +1 or -1. And then these are encoded in a vector called the spin configuration vector. Right? So this is a vector of length n, and it's just got in here all the plus and minus ones that are associated with each of the particles. Then we have for this model a Hamiltonian. And so what's happening here is that we're just summing over all the pairs of particles and this interaction, what we call the interaction coefficient, J sub ij. And the idea for this is that it's going to be modeled by a random variable, a Gaussian random variable, and they're all going to be independent except for the constraint that we should have symmetry. So J sub ij, little ij is equal to J sub little ji. You can think of this as the attraction or anti-alignment of the particles. So if the particles want to align this pair of particles, then J is going to be positive. If they want to anti-align, then it's going to be negative. And so when this Hamiltonian is large, is going to be when, for the most part, the signs of these agree if their interaction coefficient is positive, and the signs disagree if their interaction coefficient is negative. So that's the general idea, and we're trying to maximize this thing. In physics, sometimes they'll define the Hamiltonian as the negative of the quantity that I have up there, because they're trying to find a low energy system. It's the same concept. I'm just minimizing the number of negative signs that we need. But if you like it that way, you can put a negative sign here and then put another negative sign later, and it all works out the same. And we can write this just kind of to lighten the notation a bit. We can write this as a quadratic form, seen up there. Right? So now M is just the matrix that we get, and we have to do this rescaling to keep things on the same order. And this is where we see a connection to random matrix theory. So this M is a Gaussian orthogonal ensemble. If that's not something that's familiar to you, the key things to remember is that it's symmetric and that the entries are Gaussian and they're independent up to the symmetry constraint. Okay. What I want to talk about now is the spherical Sherrington-Kirkpatrick model. So this one is very closely related to what I was just talking about, but now we relax the constraint that the entries of our vector have to be plus and minus 1. So if you were to take the entries all to be plus or minus 1, this would be a vector with a norm of square root of n. So now we instead just say it has to live on the sphere of radius square root of n. So basically, we're moving from a discrete model to a continuous model. And this one is similar in certain ways to the SK model that we started out with, but certain analyses become a lot easier in this model. And one simple example of that is if you wanted to ask yourself the question, what vector will maximize this Hamiltonian? In the spherical model, that's a pretty simple question to answer. We just look at this quadratic form up here, and we say, oh, that's going to be maximized if we take this to be the leading eigenvector. But if we were working in the space where we have to have plus and minus 1 entries, almost surely that's not going, our eigenvector is not going to have plus and minus 1 entries. And so even this seemingly simple question becomes much more complicated in the discrete case. So this is one reason to work in a spherical model. It does also have some interesting applications in statistics that I'll mention a little bit later. What we're going to be focusing on today is the free energy of this model. And so the free energy is what we get when we do the exponential of the Hamiltonian that we were talking about before. We multiply it by this parameter beta, which is called the inverse temperature. And then we take the integral of that, and we take the log of the integral. So this is a kind of setup that happens in a lot of physics models. One key thing to note here is that this integrand is going to be maximized if sigma aligns with what I'm going to call U1, which is the leading eigenvector of the matrix M. And then temperature is something that's going to be important here. I'll talk just kind of heuristically about how this thing behaves at different temperatures. So beta is the inverse temperature. High temperature, we're talking about when beta is very small, when beta is close to 0. And if you look at that function up here, right, you can see that if beta was very close to 0, this integrand becomes close to 1. And so it becomes almost like a constant function. And so what that tells us is that the free energy is not going to be so sensitive to the particular choice of sigma, right, that integrand. In contrast, low temperature, so that's when beta is very large, then this integrand is going to have a spike associated with when sigma is near the leading eigenvector of that matrix. And furthermore, the height of the spike will depend on the largest eigenvalue. And so what you may guess from that is that at high temperatures, the free energy is going to depend on all the eigenvalues because the integrand is more of a flat function. Whereas at low temperatures, the free energy is going to depend mostly on the largest eigenvalue because we have this spike in the integrand. And that's more or less what happens. I'm going to give you now just like a little background on what is known about the free energy. So one of the first things that was found about this free energy is that it concentrates. It has this limiting value. So as you take n toward infinity, the free energy approaches this constant value that depends on beta. And you see there's two different formulas for it, one in the high temperature case and one in the low temperature case. And the threshold for defining high and low temperature is beta equals 1. So this SSK model was first proposed by Kosterlitz, Thallis, and Jones in 1976. And at that time, they were able to compute this limiting free energy in the setting that I've described. But this model can be generalized to many more complicated models that were studied in subsequent years. And free energy, the limiting free energy has been calculated for those as well. But it wasn't actually until 2006 that Talleyrand was able to provide rigorous proofs for all of these things. So then a logical next question coming out of this is, if we know that the free energy is concentrating around this particular value, well, what could we say about the fluctuations of the free energy? Okay, and so that question was studied by Baik and Lee in 2016. And what they found was two different results in the high and low temperature settings. So when we're in the high temperature setting, the fluctuations are Gaussian, which you can see up here. So we have a Gaussian with some explicit mean and variance. In the low temperature setting, the fluctuations are Tracy-Whittem. Tracy-Whittem distributions come up in a variety of contexts, but one context in which they come up, which is the reason that they arise here, is that they're the rescaled fluctuations of the largest eigenvalue of a random matrix. So I mentioned when I was kind of talking about the heuristics of this, that in low temperature, we expect that the largest eigenvalue is going to play some important role. And so we're seeing that here in the Tracy-Whittem distribution that arises. Okay, so a few key things to notice here. One, is that the fluctuations actually have different magnitudes. So you can see that from the normalization factors here, that we actually have smaller fluctuations at the high temperature side than at the low temperature side. And then, as I mentioned, that the high temperature fluctuations are Gaussian. It turns out they depend on all the eigenvalues, although that's not apparent from the formula here. And then on the low temperature side, the fluctuations are Tracy-Whittem depending on the largest eigenvalue. The study by Bike and Lee left open the question of what is happening at beta equals 1 at the critical temperature threshold, but they did have a conjecture, which is that there should be this critical temperature window. And so the critical temperature is beta equals 1. And what they said is that if the distance between beta and 1 is on this order of n to the minus 1/3 with square root of log n, then the fluctuations should be n to the minus 1 and square root of log n. So in between the two orders that we get in the high temperature and low temperature case. Okay. And this conjecture turns out to be true. So there's a paper by Ben that came out a few years ago. I guess the preprint of it came out a few years ago than the published version slightly more recently. And then another paper as well by another set of authors. And I present here the version from the second paper because that's kind of closer to the formulation that we used for our study, though Ben's paper proves something similar. And the setup is confirming the conjecture from the Bike and Lee paper. So they're using this this inverse temperature that's in the critical window that was conjectured. And then this is the convergence formula that they find for the fluctuations of the free energy. Okay, so there's some mean term here and some normalization, and then they actually get a Gaussian term and a Tracy-Whittem term. Okay, so what are the key things? Yes. So that's one of the key things to notice here. And that's what I have in the third bullet point here. So on the low temperature side, it's Gaussian plus Tracy-Whittem. The Tracy-Whittem actually only shows up on the low temperature side of the critical window. On the high temperature side, we just see the Gaussian, but on both sides of the critical window, the fluctuations have this order that was conjectured. The other key thing to note is that asymptotically, these two terms are independent of each other. Right. So this was the result for the SSK model, and what I would like to talk about now is the bipartite model, which is the one that we've studied. So first of all, what is the bipartite model? The SSK that we've been talking about up until now is an example of a mean field model. And so what that means is that we have these n particles and all pairs of particles are interacting with each other. In the bipartite model, instead, we have two species. So instead of just having n particles, we now have little n and little m are the sizes of the two species. And they interact only with the ones that are in the other species. So instead of having this one vector, we now have two vectors. So this one will be on the square, on the sphere in n dimensions, and this on the sphere in m dimensions. And then we're summing over pairs of particles that are from the two opposite species, and then they have these interaction coefficients. Again, the interaction coefficients are still independent Gaussian random variables, but now this matrix here will be rectangular depending on the sizes of the two species. Okay, so that's the setup. And why would we want to study this? So one reason is that it's a step away from a mean field model. Mean field models are not physically realistic in the sense that if we're talking about interactions between particles, they don't interact with all the particles, right? Usually there's some sort of geometric constraint. Maybe they interact with the particles that are near them, something like this. And so having an example of a model that is not strictly a mean field model is an interesting piece of analysis. Then another one is that this also does have applications in areas like biology and neural networks. So in the context of neural networks, this corresponds to a restricted Boltzmann machine. So there's interest in it in that sense. Bike and Lee did also study in a separate paper the free energy fluctuations of this bipartite model, and they found this really similar to what happens in the SSK model. So again, there's these Gaussian fluctuations at high temperature, the Tracy-Whittem fluctuations at low temperature, here, the critical temperature threshold is not 1, but rather it's this function, this constant that depends on the ratio of the species sizes. And so typically we take that ratio to be fixed in the asymptotics. All right, so this is the theorem that we came up with, and I highlighted in red the parts that are different from the theorem that you saw before, because the rest of it actually looks really, really similar. So in particular, right, we're looking at the bipartite model now. We have to be careful of how we do the asymptotic. So now it's not just n to infinity, but rather we have these 2 species sizes, and we want to take them towards infinity in a fixed ratio. And we call that ratio r. So that's the n over m is r plus o of n to the minus 1. Okay? And without loss of generality, we'll just assume that n is smaller or less than or equal to m. So we get r less than or equal to 1. Okay? And then we get this formula that looks quite similar to the one that you saw before. The limiting free energy is now a different formula, but we have that explicitly. And then we have an explicit constant here for the Tracy-Whittem term that depends on the ratio of the species sizes. But what we see again is this sum of Gaussian and Tracy-Whittem. And then there's the other one for comparison. Right. Okay. So that's the result that we get. I wanted to talk now a little bit about the analysis that goes into it, where all this comes from. So the key ingredient that we start off with that makes this class of models like SSK and bipartite SSK really nice is a contour integral representation that we can get for Zn. So remember, Zn, when we did the free energy, Zn, we take the log of Zn, that's the integral bit. And in the So this is what it looks like a priori in its spherical form. So we have this spherical integral for SSK. For bipartite, it looks quite similar, except that now because we have these 2 vectors, we're integrating over 2 spheres. So it's a double spherical integral. And using some Laplace transform tricks, these can be rewritten in terms of contour integrals in the complex plane, right? So this is something that's much, much easier to analyze if you compare like a spherical integral on a high dimensional surface versus just a contour integral in the complex plane. Also, these integrands depend only on the eigenvalues of the random matrix. So in the case of the SSK model, as I mentioned before, it's a GOE, a Gaussian orthogonal ensemble, is the type of matrix. For the bipartite case, it's a Wishart matrix. And so this one is, A was our rectangular interaction matrix. So that was just a rectangular matrix with IID entries. And then we take that one times its transpose, multiplying in the direction that gives us a smaller dimension. And that's our Wishart matrix. So the integral depends on the eigenvalues of that matrix. They're actually not so complicated. I think it was what I was discussing with you before. So so the G beta is so it has a beta as the coefficient, and then it's a sum over the log of Z minus eigenvalue. Another way of thinking of this is the antiderivative of the Stieltjes transform, if that's something that you're familiar with. So yeah, so it's a linear statistic in the eigenvalues. Okay. So the next step, once we have this contour integral representation, is a steepest descent analysis. Now, a priori, steepest descent analysis is something that we would apply for a deterministic function. What we need to know here is that even though our integrands are random functions, they behave closely to something more deterministic. Right? And so the idea here is that we're using properties of random matrices, in particular eigenvalue rigidity. And so these are functions of the eigenvalues of a random matrix, and we know that eigenvalues of a random matrix stay very close to their expected value, and we can use that to get a good handle on what these integrals actually look like. Okay, so there's some analysis that happens there, and then out of all of that, we obtain this asymptotic expression for the free energy. So here I didn't define D plus. D plus is the upper edge of the limiting spectral measure. So here we're working with a Wishart matrix. The spectrum of that looks like Marchenko-Pasteur distribution. If we were working with the GOE matrix as before, then it's a semicircle law. So another way to think about it is that D plus is just the limiting value of the largest eigenvalue as n to infinity. Okay. So we've got these two terms, and so I've highlighted them in two different colors. This sum of logs contributes the Gaussian fluctuations, and then this term with the lambda minus D plus contributes the Tracy-Widom distribution, the Tracy-Widom fluctuations. So this is the one that comes from the fluctuations of the largest eigenvalue. You can see the largest eigenvalue right there. And then this one maybe is not so surprising that it's Gaussian, because we're summing over some terms involving all of the different eigenvalues. And it turns out that at this scaling in this critical window that we're interested in is exactly where the magnitude of these two terms is the same. And so that's why we get the two contributions, both from Gaussian and from Tracy-Widom. Okay. The CLT part, though, is actually not so obvious. The analysis is a bit delicate because D plus is right at the spectral edge, and so you have a few terms in that sum that are going to be blowing up. And so that's what makes it difficult to analyze that one. For the SSK model, the CLT that's required is for this term here, but with eigenvalues of a GOE matrix. And so that was something that was proved recently in a couple of different papers. When we started working on this project, there was not an analogous result proved for Wishart matrices. And so that was where we kind of went on a detour to prove this other random matrix result before we could finish the spin glass project. And that's what I'll do in the second part of the talk. But one other thing that I want to mention before I go there is the asymptotic independence of these two terms. So you should be a bit concerned if I was claiming to you that these two things are truly independent, because clearly they're not. In particular, they both involve the eigenvalue lambda 1. So they're not independent, but they are asymptotically independent. And where this comes from is something that has been known for a while in a numerical setting, which is that when you take a random matrix and put it in its tridiagonal form, so the Gaussian orthogonal ensemble and the Wishart matrix both have a tridiagonal representation, which has the same eigenvalue density as the original matrix. And when you look at this tridiagonal form, you can show that, or it's observed numerically, that the largest eigenvalue actually depends only on a matrix minor of roughly n to the 1/3 size. So you have this big matrix, and then you just take the small corner, and from just the entries of that small corner, you can determine the largest eigenvalue asymptotically. But we didn't see actually a rigorous kind of theoretical explanation of why this is the case. And so the Johnstone et al. Paper showed this for GOE matrices, and then we did a project in our project show this for Wishart matrices. And it relies on using a kind of a recursive study of this tridiagonal random matrix. Right? What we get is actually n to the 1/3 times log n to the 3rd. But probably this is not completely sharp, but it was enough for what we needed. Okay. And then finally, this sum can just be determined by the rest of the matrix without that extra corner. All right, so that was, yes.
So when you take a limit of the tridiagonal, then that limit determines number 1. And that limit books the window of size n to the 1/3.
Mm-hmm.
So I think, like given that you probably don't need to log all that.
Yeah. Yeah. I mean, so I think in terms of the proof, we used the log n, but I expect that it's not needed. All right. So So now I want to, little O of n for what? Yeah, so I think the tricky part is that you have to balance these two pieces, right? So if you make the corner bigger for the largest eigenvalue, then you have to shrink the part that you're allowed to use for the sum on which you're getting the CLT. So it's going to be easier to show that I can get the largest eigenvalue from a bigger corner, but then I've got less to work with for my sum, and that part becomes harder then. Yeah, so it's sort of balanced. Yeah, so that this ended up being a nice scaling where the two things could both be proved. All right, so now I'm going to talk about the CLT result. Our goal for what we need for the spin glass project is to show a CLT for this sum here, right? So D plus is the edge of the spectrum, and then these are the eigenvalues of the Wishart matrix. What we show is actually a bit more than this. So instead of just doing this for Wigner matrices, we do this for Laguerre beta ensemble, which is a larger class of random matrices that includes the Wishart matrices that we're interested in. Then in terms of the sum, rather than just doing this sum over log of D plus minus eigenvalue, we're doing log of gamma minus eigenvalue, where gamma is allowed to depend on n, provided that it approaches D plus sufficiently fast. And I'll give a little bit more detail about that. So it could be D plus or approaching D plus sufficiently fast. Also, note this beta here for Laguerre beta ensembles is not the same beta. So this is not inverse temperature anymore. Now this just, unfortunately, people use in these two contexts use beta in two different ways. So this is a different beta. So Laguerre orthogonal ensemble, this is what I was calling before a Wishart matrix. One way to construct it is that you take an n by m matrix, which is what I'm calling A, and with IID Gaussian entries, then you multiply it with its transpose, you normalize it and by m, and you get this Laguerre orthogonal ensemble or Wishart matrix. There is another way to construct this, which is via its joint eigenvalue distribution. So we can define the set of matrices whose eigenvalues obey this density function. And this one now is, so it's this messy formula. It has beta in it. And when beta is equal to 1, this is the eigenvalue density for the Laguerre orthogonal ensemble or the Wishart matrix. So the beta equals 1 is the one that we're interested in. It's a special case of this larger class of random matrices. And again, we're focusing on the case where the n over m, which before were our species sizes, now they're just the dimensions of this matrix, are approaching our this fixed value r. And in this setting, the eigenvalues converge to Marchenko-Pasteur distribution, which is supported on the interval d minus to d plus. And so this is how the d minus and the d plus are defined, but this is the same d plus that I was talking about before. All right. So that's the setup for the Laguerre matrices. And now what we're interested in looking at with these is these log determinants. And why I call it a log determinant is this. So this is how we were writing it before. This sum of logs of eigenvalue minus gamma. But we could just as easily rewrite this. This is the log of the determinant of m minus gamma times the identity. And we're going to take, yeah.
What is the normalization of the CLT? Is there any normalization, or is it just actually the sum?
So
what is the variance of it all?
So if you put 1 over n in front of it, then it will be order square root of log n. Yeah. Yeah. Right. Sorry. Did I say that incorrectly? Yeah. No. Then sorry. That goes on the other side. Yeah. Yeah. So. Yeah. So the sorry, I meant for that to be on the other side. So this one, the fluctuations of this will be on the order of. Let's see. No, I think I said that correctly. Yeah.
I think the fluctuation left-hand side is like square root log. If gamma
Yeah.
n was a
Yeah.
spectrum, then it would just have order fluctuations.
Yes.
That's what I expect.
Yeah.
So then the CLT, the square root log n will come in there. Yeah. And so that means basically this is kind of dominated by eigenvalues that are nearby.
Okay.
I don't know. The determinant. These things are pretty subtle.
Yeah. Yeah. So gamma n will be the d plus that we were talking about before, which is one plus the square root of the ratio of n and m. So it will be close to that. It'll be that plus n to the minus something.
But if you say sum only over like yeah, it's half. If it's right, then the fluctuation of order one. So that doesn't contribute. It's not like almost right there. It's like a mesoscopic. Yeah, exactly.
Yeah.
It comes from some mesoscopic stuff.
Yeah, so it's the idea is it's sort of it falls in between in terms of its order. It falls in between what you would get from a CLT of IID random variables and what you would get from a CLT of linear eigenvalue statistic. Right, so that would be like square root of n versus 1, and here this one is square root of log n. Yeah.
It's not at all something.
No. Okay. So this is what I wanted to compare it to, which is this other result in random matrix theory. And this is like if you imagine so I told you that gamma n was going to approach the edge of the spectrum. What if we thought about instead gamma is some fixed value that's outside of the spectral support? Right, so now we don't have that issue of certain terms blowing up because gamma is like sufficiently far away from the lambda i's. Okay, and so then this one, if you subtract its mean, which is calculated from taking the integral of this against the Marchenko-Pasteur density, then you get order 1 Gaussian random variable. And so this one, if you were to contrast it with CLT that we're familiar with for IID random variables, you would expect this to have a square root of n over here, but we don't, right? And so the key here is this with eigenvalues, because of the rigidity of eigenvalues, the fluctuations are not as big as what you would see if these were just IID random variables. So this is a known result, but it doesn't apply in the case that we're looking at. And the reason is because we now have this gamma n approaching the spectral edge. And so we have certain terms that are going to give a much larger contribution. And so then this is sort of a review of some of the things that have been proved in this area. So 2 separate papers that address this for the case of Gaussian beta ensembles, which is the more generalized version of Gaussian orthogonal ensemble. And both of them kind of came at it from slightly different directions. So this one they did for Gaussian beta ensembles and then extended to Wigner matrices as well. This one of Lambert and Paquette, they did the CLT similar one for Gaussian beta ensembles, but got as a corollary of a more detailed result on characteristic polynomials. And so then finally what we do is to obtain a similar type of CLT, but for Laguerre beta ensemble. And I want to talk about, so here, there was a question about, I think you were asking about what we should assume about this gamma n. And so this is the more detailed version of it. So gamma n will be d plus, and then plus sigma n times n to the minus 2/3, where sigma n is some slowly growing function. So it can be log n squared up through log n squared. Now that by itself is not enough for the thing that we wanted in the spin glasses, right? Because for the spin glasses, we really wanted in fact that this gamma would just be D+. So we really want that sigma n to just be 0. Okay, and we didn't get that for general beta, but for beta equals 1 and beta equals 2, which are special cases, we were able to extend this not for the sigma n to be a slowly growing function, but all the way down to a negative constant. And so that includes the case of sigma n equals 0, which is the one that we need for the spin glass. But this other one is interesting in other contexts because now we have it for a larger class of ensembles. Yeah.
Does it make, can you define the spin glass models for other data here? Does it make any sense?
I mean, you can. I'm not sure. I don't know what that it would translate to.
I don't know what's here to integrate off. Trade off, and you can have some other funny ways. You know what I mean? Because when you do it for beta equals 2, you integrate over the complex sphere. When you do it for beta equals 1, you integrate over the or it's easy to generalize.
No, I think you would still just take your vectors to be on a real dimensional sphere, regardless of what the entries of the random matrix are.
Like the contour formula. I see. So you just plug in the.
Mm-hmm.
But don't you get you do a different function for GUE, where you integrate over the complex sphere?
So I don't actually remember, Ben, if you did this in your paper, but I know that the Johnstone paper, they did look at both beta equals 1 and beta equals 2, and my understanding is they're just integrating over the real sphere.
That certainly makes sense. Then I guess you can generalize this in that way.
Yeah.
So it would make sense to try to push this off.
Yeah, and in fact, I think the limitation is the methods, not that it isn't true. I think so as I said, I think I mentioned that there's 2 papers that prove this. CLT result for the GOE or the Gaussian beta ensemble, but coming at it from different angles. And so we based ours on the approach that was in the paper of Johnstone and collaborators, and they had this same issue where they proved it up until this point, and then they used for beta equals 2 some determinantal properties of random matrices, and then kind of extend that to beta equals 1. The other one, which was the paper of Lambert and Paquette, they used this approach of using a stochastic Airy function and comparing it with that, and they get it for all beta. So I expect that probably this, if we were to try it with that approach instead, perhaps we would get down to the constant for all beta. All right. So this is the CLT. This is the log determinant that we were interested in. There's a mean term, and here's the normalization, and then it converges to Gaussian. And the mean term is this very nasty thing. So it's actually, we have an expansion, asymptotic expansion here. But maybe the key thing to notice is that the leading order term is of order n for this log determinant, and the fluctuations are only of order square root of log n. And so this, I think, was what was coming up before. So sort of comparing orders of things. If you look at a CLT for IID random variables, we would expect order square root of n fluctuations. The CLT for linear spectral statistics that I was showing you before. So if we were to take the gamma and away from the spectrum, that would be just order 1 fluctuations. And here we're getting something that's in between, right? Because we have something that looked like linear, a CLT for linear spectral statistics, but then we pushed towards the spectral edge and got certain terms to become much larger.
Would you agree with my guess that this means that like the CLT comes from the 1 over log fraction of eigenvalues that are near the top edge? So you could just keep 1 over log some power eigenvalues near the top edge. Right, so what fraction of so n over 1 over n over log to some power eigenvalues near the top edge, and then your CLT comes from the fluctuations of those, and then the ones below it is.
Except that actually like contradicts. Oh no! Now I've done something weird.
Okay, so the answer is no. That's cool.
Okay. But I think right. So when I was talking about the asymptotic independence part, what we found was that if you take all but the small corner, that was actually enough to get the CLT. So in fact, we didn't need those largest ones. If we throw away a small enough portion of the largest ones, it still works.
What I'm saying is you say you can throw away a few of the top, right?
Yeah, but it was more than just a few, right? It was n to the 1/3 that we were throwing away.
Yes, but I think what it comes from is like n over log n on the top, which is much more.
Maybe.
And then everything below it is throw away.
Yeah, that is possible. Yeah. All right. So the key things I think to let's see. Okay. Yeah, I think I finished with that one. All right. So I'll briefly talk about some of the methods that went into this. And this is really also just kind of an excuse to show cool random matrix things that we found in the course of doing this. So one I've already mentioned is this tridiagonal representation for Laguerre beta ensembles. So this one is from a paper of Dimitriou and Edelman in 2002. And what they show is that the Laguerre beta ensembles can be written in this tridiagonal form. So what you do is you start with a bidiagonal matrix. So it has these A's along the diagonal and these B's below the diagonal, and everything else is zeros. And then the A's and the B's are all these chi-distributed random variables with different degrees of freedom, depending on beta and depending on the m and the n. So they change as you go down. They change based on the index. Right? And then you take this one times its transpose, and that makes a tridiagonal matrix. And this one has the same eigenvalue, joint eigenvalue density as the Laguerre beta ensemble. Right? And so that one is the basis for this analysis. What we're looking to analyze ultimately is a determinant. And right, so more specifically, this one, the determinant of this tridiagonal matrix that we got up there, and then minus multiple of the identity matrix. So what we can do is we can make a recurrence on the matrix minors. Right? So we think about the determinant of the I by I principal minor of this matrix, and then we can make this recurrence, right? So if this is the determinant of the full matrix, we can write it in terms of the determinant of the matrix that's 1 smaller and the matrix that's 2 smaller. Okay. So we have this recurrence, and then we want to analyze that to form our CLT. So the next step is to this is not a linear recurrence, so we want to transform it into something that's approximately linear. And so this is sort of rescaling that you can do based on looking at the ratio of consecutive of these determinants, and then you can make a approximately linear recurrence on that. And so the key thing here is that this coefficient of the Ri-1 is deterministic. Okay? And so that enables us to analyze this in a nice way, and the epsilon error things are small. Right, and so then there's some analysis that I won't really go into the analysis of that. It's a bit messy, but it involves some sort of concentration bounds on these chi random variables and some concentration bounds on quadratic forms involving these. And we obtained the CLT that we wanted, but only for this sigma n between log n squared and log n squared, which was not what we wanted, because we really wanted to be able to have this set the sigma n all the way down to 0. And so then here we can extend it to beta equals 2 using some determinantal properties of beta equals 2. And then this was sort of a fun thing. We can extend it to beta equals 1 by using this theorem of Forrester and Rains that connects the eigenvalues of the beta equals 2 case, which is called LUE, and the beta equals 1 case, which is called LOE. And so what their theorem shows is that if you take an LOE matrix with dimension n and m, and then you take another independent LOE matrix of size 1 larger, and then you take the union of all of their eigenvalues, and you put them in order, and then you pick out the even ones, that these will have the same distribution as the eigenvalues of an LUE matrix, which is kind of strange. But it means that if you know the eigenvalue, something about the eigenvalues of an LUE matrix, which is the beta equals 2 case, then that can help you to understand the beta equals 1 case. And so that's the key to that. And these techniques were based on what we saw in the paper of Johnstone et al. That they were doing for the Gaussian beta ensemble. So it's a similar approach, this kind of set of steps. What's different is that the Laguerre beta ensemble is more complicated to analyze due to the tridiagonal structure. So with Gaussian beta ensemble, you don't need to do this thing where you have the bidiagonal and you multiply it times its transpose. It's just a tridiagonal. All the entries are independent, whereas when you do this bidiagonal times bidiagonal, you wind up with something that has dependency between the adjacent entries and other things that just kind of make it a bit annoying. So it's a bit more complicated to analyze, but the same basic steps apply. Okay. And so I wanted to close by telling you a little bit about a statistical application of all of this, which is spiked matrix models. And so what I mean by a spiked matrix model is that we're going to, I did whatever I wasn't supposed to do. What? Control L. Okay, so I think in fact what it is just if you hold the button for too long is what causes that to happen, in case your future speakers want to avoid that. This spiked matrix model, we have H. This could be a Gaussian matrix, it could be a Wishart random matrix, but this is going to kind of represent the noise in the model. And then we have some vector here. I put it here to be deterministic. It could also be something random, but it's just a single vector times its transpose. So this makes a rank 1 matrix. And then it's multiplied by some magnitude, which gives us the magnitude of the spike or the signal. And there's well-known results about this called the BBP transition. And so what that says is that if C is above some particular threshold, in the case of Wishart matrix, it's D+. In the case of GOE matrix, it's just 1. Then if the C is larger than that, you'll have one eigenvalue which separates from the rest. And this makes it relatively easier to detect the presence of this spike because you have this one eigenvalue that's separating. But if C is below that threshold, then that doesn't happen. And sometimes you can still recover, figure out that this spike is there, but it requires some more intricate methods. And so this is where these CLTs can play a role. So the results that I've shown, the one that Johnstone et al. Did for GOE matrices, and then the one that we did for LOE matrices, these are relevant to analyzing log likelihood ratios for these critically spiked models. And we think that the LOE one is particularly interesting because of its connection with sample covariance matrices. So it's, in a sense, a better model for some statistical applications that folks would be interested in. All right, so I think that's it. Thank you.